Welcome. In this video I'll introduce a free boundary grudge runoff solver called FreeGS. This is available on GitHub and has some documentation on Read the Docs. It's easily installable from the command line with pip using this command, and the version I'm showing you here is 0.1.6, so that was from this year, 2019. Future versions should work as well, and you should be able to download this notebook and then play around with it yourself. So it's solving the Grudge-Runoff equation, which is for force balance in a tokamak or toroidal plasma. And so we're solving an elliptic equation on the left-hand side. It's basically like a Laplacian, but in toroidal coordinates. And on the right-hand side, we have an equation for the current. So J phi is the current in the toroidal direction, which is a function of r and z, and crucially also depends on psi. So it depends on these properties. So P, pressure as a function of psi, and F, which is r times toroidal field as a function of psi. And so as psi is changed, the current also changes. And so it's a nonlinear partial differential equation. So you've seen previous videos, I tried to explain how the different components of this code work. And so here I'll show you in practice how we use them. So of course, first import the module. Then we can define where the coils and what the machine is. So there are various components you can use, so coil and machine, which contains a set of coils. Here we just define a list, and it's one basically name for each coil. And then here we have a coil object, and we just specify what the major radius and the height, so this is r and z in meters. If you need to, you can join these together into circuits. So for example, these are in pairs. So we have both at r equals 1 and z is plus or minus 1.1 meters. In many tokamaks, the coils are wired in pairs, so the upper coils are connected in series to the lower coils, and so this would be these two could be joined together into a circuit. So I'll show you how to do that a bit later. And similarly for the lower coils, we could wire these into a circuit as well. And then when we find our coils, we put them together into a machine, into a tokamak, and calling this tokamak in the later cells. Okay, so then a crucial part is to specify these profiles, pressure and poloidal current function F, which determine the toroidal current. And there's the very nice paper which explains most of these steps on this archived link here, which uses the same profiles. And so if you look at this function, it's a function which depends on major radius, and a function which depends on the inverse of major radius. And so what we do is we write the toroidal current as a constant times major radius, and another constant times 1 over major radius. And this is multiplied by a shape function which only depends on psi. And so by tuning this parameter beta naught, and by tuning this factor lambda, we can vary essentially whether the current is due to the pressure gradient or due to this F. And we can change the shape of the current profile by modifying this J tilde shape function. And the shape function is written like this. So it has two parameters, alpha m and alpha n, which just change the steepness of the function. And it's a function of normalized psi. So this psi n is 0 on the magnetic axis, so when psi is equal to psi on the axis, and it's 1 when psi is equal to the boundary, psi on the boundary. So you see that J goes from 1 when psi n is 0 on the axis to 0 at the edge, and so we have no current beyond the edge of the plasma. So to get the current, we need two constants. We have this lambda and the beta naught, and these are determined by two constraints. So here we specify the maximum pressure and the plasma current. The plasma current, for example, is the integral over the whole cross-section of the toroidal current, and so using that we can get a constraint for lambda. And similarly, there's an integral over the whole domain which gives you the plasma pressure, and that can give you again a constraint for beta. Okay, so here this is how this is done in FreeGS. So we create an object we call profiles. It's using a system where we're constraining the pressure on the axis and plasma current, IP. We specify the pressure in pascals, the current in amps, and then this is specifying the toroidal field. So it's the R times toroidal field in the vacuum. So if there was no plasma. Okay, so that defines the P and the F profiles. Then a crucial part is controlling the currents in the coils. So we said where the coils are, but not what the currents are. And we need a control system to sort out the shape of the plasma. And this is done mainly by saying where you want X points. These are R and Z locations. So this is major radius and height for 2 X points. And these are isoflux locations, so they're pairs of RZ, so this is the first, like R1, Z1. So this is R is 1.1, Z is minus 0.6, and we're constraining that to be the same psi as R is 1.1, Z is plus 0.6. So it will try and constrain these two to be equal. And that's done using a control system. So here we specify we want to constrain these X points and these isoflux constraints. And that gets put into a constraint object. Okay, so now we can put together all the pieces. So we have the coils, we have the profiles and the control system, and we need a grid or a mesh to solve it on. So we specify we have an equilibrium which is based on this tokamak. It has this range of R and Z and this number of grid points. And remember, these are this is a fairly typical kind of value. Remember, these are 2 to the n plus 1, so it's 64 plus 1, because that enables some more efficient numerical algorithms to be used. Here we specify then the boundary. So we're using von Hagenau's method, which remember is a slightly more efficient method when you have large grid cells. There's also a Green's function method for comparison. And then finally, we solve the full system using Picard iteration, using the given equilibrium, so the mesh, the profiles, and the constraints, so the control system. This then runs through a set of iterations. So each time it's calculating the change in the current. So this is an array of all the currents that we're changing, and calculating the constraints, so for the profiles. These are the lambda and beta naughts. And then as these iterations proceed, you can see that the change in the currents becomes smaller and smaller. So we go down towards the end. You see the change in beta naughts, for example, here has become quite small, and similarly for L, lambda. And the changes in currents are now much smaller than they were previously, so it's now changing by hundreds of amps, whereas it was changing by tens of thousands of amps. So the iterations get closer and closer to the real solution. We could continue this by giving it a smaller tolerance, and then the iterations would keep going. Okay, then finally, we've got equilibrium. We can now plot it. So there's a routine in plotting, which plot things. So this is plotting an equilibrium. You can see here's the poloidal flux. It's picked out the separatrix here in red, and the locations of the X points in red here. So one is at minus 0.6 and 1.1, and one is at plus 0.8, and again R of 1.1. These are the two locations we asked for. And then the two constraints we were specifying were that this point was linked to that point here. So plus minus 0.6. So we've specified a lower single null X point configuration. Okay, there's other diagnostics we can look at. So you can print the currents in the coils, for example, by looking at the machine, so the tokamak object. So this contains the set of coils we created. So we specified the R and Z locations. The control system has calculated the currents. We didn't specify the number of turns in the coil, so typically each coil will be made up of many turns. In general, we could specify how many turns you want in the coil. And so this is the total current, so 234 kiloamps running through a single coil. If you had more turns, of course, then this would be divided by the number of turns. And then this just specifies that this coil is under feedback control. So if you create a coil, you can specify control equals false, and this will switch off the feedback control for that coil, and then you just specify what current you want. So you can fix the current if you desire. An important constraint is the forces on all these coils. These are carrying very large currents. The plasma itself is carrying a very large current, and so the forces can be quite large. There are forces due to the plasma, of course, so the plasma is creating a magnetic field, and that's interacting with the current in the coil. There are the fields due to the other coils, and perhaps most difficult to calculate is the force due to itself. This is because if you have a circular coil carrying a current, there's a magnetic pressure inside the coil which is larger than the pressure outside. Or you can think of each element of the coil as being has a force on it due to the other elements of the coil. So, for example, the part of the coil that's on the opposite side, and so the coil will tend to expand and experience a force, this hoop force, and this depends on the cross-section area of the coil. So here, A here is the minor radius of the coil, and this psi here is the internal inductance. That depends on the current profile inside the coil. So it's a half, for example, if the current is steady state. So here we're assuming a constant current, and so we use psi as a half. If you have a rapidly changing current, then the current is mainly on the surface, and then psi goes to 0 if you have a surface current. The main effect is the major radius of the coil and the cross-section area, so the minor radius. And then you see that the force goes like the current squared, because the magnetic field it's producing goes like current, and then the force is like current times magnetic field. So if you're designing a tokamak, this is a bit uncertain what to set this to. You can specify an area if you know what it is. So you can just say, when you create a tokamak, you can say this coil has an area of in this case in meters squared. You'd also specify it as a current density limit. So at the moment what's done is we specify a current density limit for niobium tin superconductor, use that to calculate the cross-section area, and then use that area to calculate the force. So this is an overestimate of the force, because in reality you'd have a larger area, but this is kind of an upper limit for the force. There's a paper here showing how this is derived. What's in the Landau-Lifshitz, if you're familiar with that. So you can print the forces. These are the forces on all the coils. And this is the force in the radial direction and the force in the vertical direction. And of course the force in the vertical direction should approximately add up to 0, depending on how accurate the solution is. But the force in the radial direction do not, and in general the forces are outwards. But you can see they can be very large. And a large part of that is the self hoop force. Finally, an important plasma parameter is the safety factor, which is calculated by the number of toroidal turns a magnetic field line experiences for one poloidal turn. So it's the integral over the poloidal angle theta of the change in toroidal angle with change. So this is the change in toroidal angle along the field line. This is the change in poloidal angle along the field line. So the integral of these gives you the number of times the field line moved toroidally. So you can calculate this again with the equilibrium object. You can just call Q, and so either you can specify a normalized psi. So here psi is going from essentially on the axis to close to the edge. So point 1 would be the edge of the plasma. But at the edge of the plasma there's a separatrix, so there's an x point, and so this integral goes to infinity. And so we just go close to the edge but not at the edge. And same in the core, calculate this integral becomes quite inaccurate, and so 0 is also not very accurate value to use. So we can print some values, and this is what's shown here. So you see it's going from just less than 1 in the core out to about 5 or so at psi normal of 0.95, and we can just plot. So if you don't give a value of psi n, it creates a grid and passes back a range of values. And so we can plot this, and this is psi normal, so from the axis to the edge, and this is the safety factor. And this is a fairly typical kind of shape. Finally, we can specify that we can ask for the plasma current. In this case, we constrained the plasma current to be 300 kiloamps, and that's what we've got to within numerical error. We can then ask for the poloidal beta, which here we didn't constrain because we constrained the plasma pressure. You can see here we've got 2% poloidal beta. You could constrain the poloidal beta, and then obviously that should come out as the value you've constrained it to. Okay, so now we can try playing around with this a little bit. So we can try, for example, changing locations of the X points. And you see how the equilibrium changes. So I'll run this again. This will run through some iterations. And again, plot this one. And now we have an up-down symmetric equilibrium because you have constraints on the psi and constraints on two X points being the same. We can see how the currents change. You can see now we've essentially got the same currents in the top and the bottom coils. And again, we can print the forces, which now are equally balanced, top and bottom. And the safety factor as well. So we can run this. You can see the safety factor has dropped slightly, at least in the core. As poloidal beta. Okay, so there can be various knock-on effects of changing the shape of the plasma on the other plasma quantities.